Good day to you, students. How's the day going? Today we'll be dealing with chapter 20 in physics, electromagnetic forces. The magnetic effect of a current or the magnetic effect of an electronic or electrical current. Electromagnets can be made by passing a current through a coil of wire. This coil of wire is known as a solenoid. The flow of current results in a magnetic field around a solenoid. The field is similar to the field around a bar magnet. The field lines are circles around the current. Every electrical current is surrounded by a magnetic field that creates it. The right hand grip rule tells about the direction of the field lines. This is all in relation to what we call the Ampere's law. As you can see from this diagram, it has a length, and this wire is one round, that is made to encircle around this particular coil in this particular direction. That wire is known as a solenoid. It generates electrical current, and around it, the magnetic field is being felt. So the magnetic effect of a current, we are still dealing with that. All these materials use electromagnets except electric heater, induction cooker, headphones, generator. If you look at a generator has an electric motor. So an electric motor must have a solenoid. The same thing with an headphone. The same thing with induction cooker, but never an electric heater. So an electric heater does not have an electromagnet. Now, comparing magnetic fields. Magnetic field is represented by drawing field lines. The arrows on the lines show the direction of the field at any point. Now, this arrow is the direction of the force on a north magnetic pole placed in the field. Now, the magnetic field associated with a solenoid runs from the magnetic north pole to the south pole. Now, looking at this diagram on the right, this is a typical illustration of an electric bell. Now, for an electric bell, current flows through the wire. It has a better push, which is more or less like the switch. Then it has an electromagnet in which wires are wound around it. That is wire encircled, just like performing the role of a solenoid. And we also have springy metal strip, the contact strip, the soft armature made from iron. We have hammer and the gong. When the hammer strikes the gong, the noise is then produced for the electric bell to act. We are still dealing with how to compare magnetic fields. How do field patterns compare? Now, we'll first of all deal with the current that is available in the wire, just like we saw from the last diagram. The field lines are circles around the wire. If the current is greater, the field will be stronger, and so the lines will be closer together. If you reverse the current, you are reversing the direction of the field. Now, current in a solenoid. The field lines are close together at the poles of the electromagnet. Inside the coil, the field lines run parallel to each other, showing that the field is uniform. Increasing the current gives a stronger field. Reversing the current reverses the field. Now, looking at this diagram, I can place this bar magnet inside this solenoid and determines how the current will move around the circuit. You can see the induced current direction. So far the what? Bar magnet comes into the what? Coil of the what? Electromagnet. Now coil will the coil will have n number of turns and also a cross-sectional area A. And for the magnet from the north to the south pole, magnetic field B is moving to the what? To the left hand side. That's the direction. Don't forget that magnetic field is represented with what? Letter B. It has magnitude, it also has direction. Now, let's deal with this question. This is a typical solenoid with a bar magnet beside it. The diagram above, which of the following would give a zero reading on the voltmeter? Now, holding the magnet stationary inside the solenoid, that's true, because for the solenoid and the back magnet, for it to give a reading on the voltmeter, the magnet ought to be coming in and going out of the solenoid, of the wound wires. It has to be coming in and going out, coming in and going out. So let's look at other options. Moving the magnet away from the solenoid, that is not possible. Moving the magnet towards the solenoid. Not only that, it has to be removed immediately. It goes in and comes out, goes in and comes out. Then moving the solenoid towards the magnet, that's not feasible. So you have to hold the magnet stationary inside the what? Solenoid. If it is to give a zero reading on the voltmeter. So let's check. That is it. Now, how electric motors are constructed. The electric motor has certain features. They are a coil of wire, as we can see from the second diagram that is beneath. Two magnets, the one having south pole and the other having north pole. We also have split ring commutator, as you can see, which is divided, one on the right, the other on the left, and two brushes, as you can also see, one on the left, one on the right, which are springy wires that press against the two metal sections of the commutator. Now, how does electric motor works? A current flows through the right hand brush into the what? Circuit. Current in. It is available in this diagram. When the current is flowing, it becomes an electromagnet. And the coil that we can see here starts to turn anti-clockwise. This particular coil that has black shape starts to turn anti-clockwise. That means it goes from the what? The right hand side to the left hand side, from the northern pole to the southern pole. The current flows the opposite way around the coil. That means the current flows from the right hand side also to the left hand side. So which of these ways do not make a motor, that is an electric motor, powerful? A, by making the permanent magnet stronger. Yes. B, shortening the wire of the electromagnet. That's a no. You have to lengthen the wire of the electromagnet, because by the time the wires are worn, it will serve as what? As a solenoid. And a solenoid will have what? A very strong magnetic field. Now, option C, by adding more turns of wire on the coil. Yes. By increasing the current in the electromagnet. Yes. So the right option will be shortening the wire of the electromagnet. That is it. Now, first, on a current carrying conductor. An electric motor has a coil with a current flowing around it in a magnetic field. Two magnetic fields interact with each other. A magnetic field and a current flowing across the what? Magnetic field. The two magnets in an electric motor provides a vertical magnetic field. The force in the magnetic field of an electric motor can be increased in two ways. Again, the force in the magnetic field of an electric motor can be increased in two ways. A, by increasing the current, and B, by using magnets with a strong magnetic field. Now, looking at this diagram, this is the direction of the force on wire, this is the direction of the magnetic field, and this is the direction of the what? Electric current. You can see that the force on the wire is perpendicular to the electric current, while the magnetic field cut across or act across the force on wire and the electric field. Forces made use of by electric motor is known as the motor effect. So that is what? True. Let's check. Correct. Now, we're still dealing with electric motor. Force caused by an electric motor is reversed. If the direction of the current is reversed, B, the direction of the magnetic field is reversed. That means the force of an electric motor depends on the current and the magnetic field. Okay, so let's deal with this question. From the diagram above, the function of the split ring commutator, as you can see, is to reverse the current every 180 degrees and makes connection with the rotor coil. That is what? True. So we check. That's correct. Now, Fleming's left-hand rule. There are three things with direction, vector quantities that we need to take note when dealing with Fleming's left-hand rule. They are the magnetic field, the current, and the force. Now, if you look at the magnetic field, it is what? Vertical. Alright? The current and the force are horizontal and are at right angles to each other. Fleming's left-hand rule is used to predict the direction of the force on a current-carrying conductor in a magnetic field. Let me state it again. Fleming's left-hand rule is used to predict the direction of the force on a current-carrying conductor in a magnetic field. This has been illustrated with the use of what? The thumb, the first finger, and the second finger. The first is always on the thumb. First finger takes the magnetic field, and the second finger the what? Current. Force on a conductor placed in a uniform magnetic field can be increased with. Force on a conductor placed in a uniform magnetic field can be increased with. That means here now, from the later slide that we dealt with, we saw how force was in horizontal position alongside with the what? Current. So if I need to increase my force, I will also increase the what? Current. So the right answer will be that what? Increase in current. Now, electron beams and magnetic field. A magnetic field can be used to detect beams of electrons. This can be demonstrated with the use of vacuum tubes. In the vacuum tubes, electrons move from left to right. The magnetic field is pointing towards the front. So the force must be what? Upwards. When a current carrying conductor is placed in a magnetic field, it is the electrons that feel the force. Electrons that transmit the force then transmit the force to the conductor. As you can see in this diagram, electrons are moving from the left hand side to the right hand side with the use of the what? Vacuum tubes, which has been photographed above here. Now, let's deal with the correct statement before we wrap it up for today. The flow of voltage results in electric field around a solenoid. That is wrong. The flow of electric current results in a magnetic field around a solenoid. Very correct. The last statement, the flow of electromotive force, that is the voltage or the potential difference results in a magnetic field around a bound magnet. That is also false. So the correct option would be that the flow of electric current results in a magnetic field around a solenoid or a current carrying conductor. So we've come to the end of this class. Do well to join our website www.edubbey.com for more of our interactive notes and classes. Subscribe. Bye for now.